The universe has often been described by poets, philosophers, and scientists as vast, infinite, and eternal. Yet, beneath this seemingly static infinity, modern science reveals a different reality. The universe is not still. It is alive with motion, transformation, and expansion, behaving more like a dynamic organism than a frozen backdrop. This restless activity occurs on all scales, from the tiny fluctuations of subatomic particles to the largest cosmic structures that span billions of light years. To understand why the Boötes Void, the largest known empty region in the universe, exists, we must first appreciate that the universe is fundamentally a living, changing system, constantly evolving and reshaping itself. For thousands of years, humanity gazed at the night sky and believed it to be fixed and eternal. Stars appeared every night in their familiar patterns. Planets traced their predictable paths, and galaxies, though unseen by ancient eyes, held their place silently in the darkness. The worldview was that the heavens were unchanging, a grand clockwork designed to run endlessly in the same manner. But this view has been completely overturned in the last century of astronomy. We now know that the universe itself has a history, that it was born in a fiery beginning 13.8 billion years ago, and that ever since it has been evolving. The stars are not eternal. They are born, they live, and they die. Galaxies collide and merge. Structures rise and dissolve. At the grandest level, the very fabric of space itself stretches and grows larger, pulling galaxies farther apart with time. This expansion is not a slow drift, but an acceleration, like a river picking up speed as it rushes toward an unseen destination. In the early years after the Big Bang, gravity tried to hold the expansion in check, slowing it down as matter pulled on matter. For billions of years, this tug-of-war defined the cosmic pace. But then, several billion years ago, something unexpected happened. The expansion began to accelerate. Instead of slowing under the weight of gravity, the universe seemed to gain energy, driving galaxies apart at a faster and faster rate. This mysterious force, which we now call dark energy, changed our entire understanding of cosmic evolution. The fact that the universe is expanding and that this expansion is speeding up affects everything we observe. It affects individual galaxies as they are carried away from one another by the flow of expanding space. It affects galaxy clusters, which fight to stay bound together under the pull of their collective gravity while expansion works to pull them apart. It affects the largest structures, the great filaments and sheets of the cosmic web, stretching them thinner with time. Most importantly, it affects the voids, the great empty spaces between the filaments, because voids are the regions where expansion dominates most clearly. The Boötes Void is a prime example of this process. Its vast emptiness was not simply born that way, but was shaped and exaggerated by billions of years of cosmic expansion. To visualize the living nature of the universe, imagine standing in the middle of a field full of balloons being inflated at the same time. Each balloon grows larger and pushes against the others, changing the arrangement constantly. Now imagine that instead of balloons, the entire space of the field is stretching, carrying points farther apart without them actively moving. This is what the universe is doing. Galaxies are like dots drawn on the surface of a balloon. They are not moving themselves, but are carried apart as the balloon expands. The expansion itself is invisible. It is not a wind or a force pushing galaxies through space. Instead, it is space itself stretching, a growth of the distance between objects. This expansion has been confirmed through one of the most powerful discoveries in astronomy, the redshift of light. Light, traveling across space, is stretched as the universe expands, shifting it toward longer, redder wavelengths. When astronomers look at galaxies far away, they see this redshift. The farther away a galaxy is, the faster it appears to be moving from us. This relationship, discovered by Edwin Hubble, gave birth to the modern understanding of an expanding universe. It also shattered the old belief that the cosmos was static, Instead, it revealed that the universe is more like a breathing organism, in a constant state of change. This living quality of the universe also applies to smaller structures. Stars, for example, are born from collapsing clouds of gas, live for millions or billions of years, and then end in spectacular deaths, scattering heavy elements across space. These cycles of birth and death enrich galaxies with the ingredients for planets and eventually life. Galaxies themselves are dynamic entities interacting and merging with one another. The Milky Way is currently on a slow collision course with the Andromeda Galaxy, a cosmic dance that will reshape both galaxies into one massive elliptical galaxy billions of years from now. Nothing in the universe is still. Even what appears fixed to us is, in truth, moving and evolving on scales too vast for human eyes to detect. But the most profound expression of this constant change is the structure of the universe itself. On the largest scales, matter in the universe forms a web-like pattern, vast filaments of galaxies and dark matter stretching across billions of light-years, connected at nodes where clusters of galaxies reside. Between these filaments are enormous voids, where little matter exists. These voids are not empty in the absolute sense. They contain stray galaxies, thin gas, and dark matter, but compared to the filaments, they are astonishingly barren. The Boötes Void, in particular, is so empty that it defies ordinary imagination. It is nearly 330 million light-years across, with only a handful of galaxies scattered inside. To grasp this size, consider that our entire Milky Way galaxy is just over 100,000 light-years wide. The Boötes Void could contain thousands of Milky Way galaxies lined up side by side, yet it is almost empty. The existence of such a vast emptiness is not an accident. It is a result of the dynamic universe. As space expands, regions with less matter grow emptier because there is less gravitational pull to hold them together. Matter is drawn toward filaments and clusters, leaving voids increasingly desolate. The universe is sculpted by this dance of gravity and expansion, creating the cosmic web we observe today. Without expansion, voids like Boötes would not exist in their current form. The universe would have collapsed into a far denser and more uniform structure. What makes this even more astonishing is that expansion is not slowing but accelerating. This means that voids are not only large now, but will continue to grow, swallowing up more regions as galaxies are pulled farther apart. The Boötes Void, already immense, is destined to become even more desolate in the future. In billions of years, any galaxies within it may find themselves utterly isolated, unable to see or communicate with galaxies outside their local region, as the accelerating expansion carries them beyond the cosmic horizon. Thus, when we speak of the universe as living, it is not poetic exaggeration. The universe is alive with processes of growth, expansion, evolution, and change. Just as a living organism develops, adapts, and transforms, so too does the cosmos. This living quality explains why voids exist, why they grow, and why studying them gives us insight into the most fundamental forces shaping reality. The Boötes Void is not merely a strange empty hole in space. It is a monument to the living nature of the universe, a product of billions of years of motion and change. To understand its existence is to recognize that the universe itself is never still, that its very essence is transformation. Expansion is not just a feature of the universe, it is the heartbeat of the cosmos, driving the creation of structure, the growth of emptiness, and the endless reshaping of reality. In the story of the universe, stillness is an illusion. Everything moves, everything changes, and everything is connected by the restless energy of expansion. From the stars in our skies to the incomprehensible voids between galaxies, the universe is alive, living, breathing, and forever changing. The universe is a grand stage where two of the most fundamental forces of nature are constantly at work: gravity and the expansion of space. These forces are not abstract concepts, but real, measurable phenomena that have shaped the cosmos from its earliest moments to the vast structure we see today. Understanding how gravity and expansion interact is key to comprehending why the universe looks the way it does, why cosmic voids exist, and why empty regions like the Boötes Void are so extreme and striking. Gravity is perhaps the most familiar of these forces, though its cosmic implications are far beyond everyday experience. Sir Isaac Newton first formulated the law of universal gravitation in the 17th century, describing how every object with mass attracts every other object. While Newton could not have imagined the vast scale of the cosmos, his principles apply universally. On Earth, gravity keeps us anchored to the surface. In the solar system, it governs the orbits of planets around the Sun. On galactic scales, it holds stars together within galaxies and binds galaxies together within clusters. Gravity acts as a cosmic glue, pulling matter together and forming the structures that give the universe its recognizable shape. In the early universe, shortly after the Big Bang, gravity played a crucial role in organizing matter. At that time, the cosmos was nearly uniform, with tiny fluctuations in density, areas slightly denser than average and others slightly emptier. These minute variations were seeds that gravity amplified over billions of years. In regions with a little more matter, gravity began pulling surrounding material inward. Gas clouds collapsed to form the first stars and galaxies themselves began to cluster together, forming groups and eventually superclusters. Over time, the gravitational pull of these dense regions grew stronger, attracting more and more matter and shaping the cosmic web. But gravity is only one half of the story. While it pulls matter together, the universe itself is expanding, stretching the fabric of space between galaxies. This expansion was first discovered by Edwin Hubble in the 1920s, when he observed that distant galaxies were moving away from us, with those farther away receding faster than those nearby. Initially, astronomers believed that gravity might eventually slow or even reverse this expansion, causing the universe to collapse in a big crunch. However, observations in the late 20th century revealed a stunning truth. The expansion is accelerating. The universe is not only growing larger, but doing so faster over time, driven by a mysterious force now known as dark energy. Gravity and expansion are thus opposing forces, locked in a cosmic tug-of-war. Gravity works to pull matter together, building stars, galaxies, and clusters. Expansion, on the other hand, stretches the space between these structures, working to pull everything apart. The balance between these forces depends on location and scale. In dense regions of the universe, gravity dominates. Galaxies are bound together, clusters remain intact, and the pull of gravity can largely counteract the expansion of space. In contrast, in areas where matter is sparse, gravity is weak. Here, the expansion of space takes over, stretching regions of emptiness and creating cosmic voids. Cosmic voids are perhaps the most dramatic evidence of this interaction. They are enormous regions of space where matter is extremely scarce, sometimes containing only a handful of galaxies across hundreds of millions of light years. The Boötes Void is one of the most famous examples. Measuring roughly 330 million light years across, it is nearly empty, with very few galaxies inside. Its existence highlights the power of expansion to dominate in underdense regions, effectively pushing matter outward and leaving behind a vast, desolate space. To visualize the effects of gravity versus expansion, imagine a network of interconnected springs with small beads attached at various points. The beads represent galaxies or clusters of galaxies, while the springs represent the underlying structure of space. Gravity acts like a glue holding beads together at the nodes, keeping clusters intact. Expansion is like pulling the entire network from the edges, stretching the springs and increasing the distances between beads. In dense areas, the glue of gravity keeps beads together despite the stretching. In sparse areas, where beads are few and far apart, the expansion dominates and the gaps grow ever larger. The dynamic interplay of these forces also explains the shape and distribution of voids. Most voids are not perfect spheres. They are stretched, twisted, and irregular. This is because gravity pulls matter away unevenly. Denser regions attract more matter, while less dense regions are left increasingly empty. Over billions of years, the expansion magnifies these differences, creating voids that can span hundreds of millions of light years. The Boötes Void, with its remarkable emptiness and irregular shape, is a prime example of this process. Gravity and expansion also affect the galaxies that do exist within voids. Even the few isolated galaxies in regions like the Boötes Void are influenced by the surrounding emptiness. With so little matter nearby, gravity is weak, and these galaxies can drift slowly apart. Their evolution differs from galaxies in clusters, which are constantly interacting, colliding, and merging with neighbors. In voids, galaxies experience fewer interactions, leading to unique structures and slower evolutionary processes. Studying these isolated galaxies helps astronomers understand how environment affects galaxy formation and growth. The effect of expansion is not uniform across the universe. In the densest clusters, gravity can nearly counteract the expansion, keeping galaxies tightly bound. In filaments of the cosmic web, the tug-of-war is ongoing. Matter is slowly pulled toward the nodes while space continues to stretch. In voids, however, the balance tips entirely in favor of expansion. The Boötes Void, along with other large voids, demonstrates the extreme outcome of this cosmic push. The few galaxies present are effectively left behind as space stretches around them, increasing the size of the void over time. This interaction has profound implications for our understanding of the universe. By observing how voids expand and evolve, scientists can study the properties of dark energy. In crowded regions, gravity can mask the effects of dark energy, making it difficult to measure. But in voids, where gravity is weak, the influence of dark energy is clear. The growth of voids provides a natural laboratory to test theories about the expansion of the universe and the ultimate fate of cosmic structures. Moreover, gravity and expansion together explain why the universe is a patchwork of matter and emptiness rather than a uniform field. Dense regions form galaxies and clusters, creating the luminous parts of the cosmos, while underdense regions become voids. The result is a cosmic web, a sponge-like structure with filaments, nodes, and vast empty spaces. Voids like the Boötes Void are not anomalies but essential features of this structure, providing insight into the large-scale forces that shape everything from stars to superclusters. The interplay of gravity and expansion also has temporal implications. In the early universe, gravity dominated more strongly because matter was more concentrated. Over time, as space expanded and matter became more spread out, the influence of gravity weakened in certain regions, allowing expansion to dominate in voids. This dynamic balance continues today, shaping the universe in real time. As the universe ages, voids grow, filaments stretch, and isolated galaxies drift further apart. The Boötes Void, already enormous, continues to expand, exemplifying the long-term effects of this cosmic tug-of-war. Even on the human scale, these forces affect what we see when we look into the night sky. The expansion of space stretches light from distant galaxies, shifting it toward longer wavelengths. This redshift allows astronomers to measure how fast galaxies are moving away from us, providing direct evidence of the accelerating expansion. Gravity, meanwhile, bends light through a phenomenon known as gravitational lensing, allowing us to map mass in the universe, including dark matter. Together, these forces govern the motion of galaxies, the growth of structures, and the evolution of cosmic voids. Gravity and expansion are the twin sculptors of the cosmos. Gravity pulls matter together, forming stars, galaxies, and clusters, while the expansion of space stretches the universe, particularly in regions of low density. This push and pull creates the rich, web-like structure of the cosmos, with luminous filaments and vast haunting voids. The Boötes Void is an extreme example of this process, a vast emptiness created by the dominance of expansion over gravity. By studying it, scientists gain insight into the fundamental forces shaping the universe and the role that emptiness plays in cosmic evolution. Gravity and expansion are not merely forces, they are the architects of reality itself, dictating how matter, energy, and space interact to produce the universe we observe today. The story of the expanding universe begins with one man, an American astronomer named Edwin Hubble, whose work in the late 1920s fundamentally changed humanity's understanding of the cosmos. Before Hubble, the prevailing view of the universe was limited and often Earth-centric. Astronomers assumed that the Milky Way was the entire universe. Other faint fuzzy patches of light observed in the night sky, known as nebulae, were thought by many to be simply gas clouds within our galaxy. It was a universe that appeared static, unchanging and finite, a tranquil, eternal stage on which stars and planets existed. Hubble's work challenged this view and opened the door to a radically new understanding. The universe was not static. It was dynamic, ever-expanding and enormous beyond comprehension. His discovery laid the groundwork for modern cosmology and transformed our perception of space, time, and our place in the cosmos. The journey to Hubble's discovery began with the need to measure distances in the universe. Determining how far away celestial objects are is one of the most challenging tasks in astronomy. The apparent brightness of a star or galaxy alone is not enough, because intrinsic luminosity varies. Hubble relied on a method known as the standard candle technique, which involves objects of known brightness, allowing astronomers to calculate distance based on how dim they appear from Earth. One particularly important standard candle is the Cepheid variable star. These are stars whose brightness oscillates with a predictable period. By measuring the period of a Cepheid's brightness cycle, Hubble could determine its true luminosity, and from that, calculate its distance. By carefully observing Cepheids in distant nebulae, Hubble demonstrated that many of these objects were far outside the Milky Way. This alone was revolutionary. It confirmed that the universe was far larger than previously imagined, containing countless galaxies beyond our own. For the first time, the scale of the universe expanded dramatically in human understanding, from a single galaxy to a cosmos filled with billions of galaxies spread across unimaginable distances. But Hubble's greatest contribution came from combining distance measurements with observations of galaxy motion. Using spectroscopy, astronomers can measure the wavelength of light emitted by stars and galaxies. When an object moves toward us, its light is compressed, shifting to shorter wavelengths, a phenomenon called blue shift. When an object moves away, its light stretches to longer wavelengths, creating a redshift. Redshift is essentially a Doppler effect for light. Hubble observed the light from numerous galaxies and measured how much their light had been redshifted. What he discovered was astounding. Nearly every galaxy he studied was moving away from Earth. More strikingly, there was a clear relationship between a galaxy's distance and its speed. The farther away a galaxy was, the faster it appeared to recede. This relationship is now known as Hubble's law and is expressed mathematically as v equals h0 times d, where v is the galaxy's recessional velocity, d is its distance, and h0 is the Hubble constant, the rate of expansion of the universe. Hubble's law was not just a formula, it was a profound statement about the nature of space itself. It is crucial to understand what Hubble's law truly means. Galaxies are not flying apart through pre-existing space like shrapnel from an explosion. Instead, it is space itself that is stretching, carrying galaxies along with it. This distinction is subtle but essential. Imagine drawing dots on a balloon and inflating it. The dots represent galaxies. As the balloon expands, the dots move away from each other, not because they are traveling through the balloon, but because the balloon itself is stretching. Similarly, the space between galaxies stretches, causing them to recede from each other. The farther apart the galaxies are, the more space there is to stretch, and the faster the separation occurs. This simple yet profound insight explains why distant galaxies recede faster than nearby ones. Hubble's discovery also had implications for our understanding of cosmic time and the universe's origin. If the universe is expanding, then logically it must have been smaller in the past. Rewinding this expansion leads to the concept of the Big Bang, the singular beginning of the universe from an extremely hot, dense state. Hubble's observations provided the first empirical evidence that the cosmos is dynamic and that space itself evolves over time. The implications of Hubble's work extend even further. The expansion of space affects every scale, from the movement of individual galaxies to the structure of the entire universe. On small scales, gravity dominates. Planets orbit stars, stars orbit galactic centers, and galaxies within clusters remain gravitationally bound. Expansion has negligible effect here, but on very large scales, beyond clusters and superclusters, gravity weakens and expansion becomes the dominant force. This is why cosmic voids, vast regions of nearly empty space like the Boötes Void, can grow so large. In these underdense regions, gravity is too weak to resist the stretching of space. Over billions of years, expansion pushes galaxies even farther apart, creating enormous empty regions and shaping the cosmic web. Hubble's law also provides a method for estimating the age of the universe. If the universe is expanding, one can conceptually run the clock backward to determine when all matter would have been concentrated in a single point. Using measurements of the Hubble constant, scientists estimate the universe is roughly 13.8 billion years old. This remarkable conclusion ties directly back to Hubble's initial observations and illustrates the enduring impact of his work. The concept of redshift, central to Hubble's discovery, has profound implications for observing the universe. Light from distant galaxies is stretched not only in wavelength, but also in time. This means that when we observe galaxies billions of light years away, we are seeing them as they were billions of years ago, not as they are today. The universe, in effect, becomes a cosmic time machine. Hubble's measurements allowed astronomers to begin reconstructing the history of cosmic expansion, galaxy formation, and the large-scale structure of the universe. Hubble's discovery also intersects with the concept of dark energy. Although Hubble could not have known about dark energy in the 1920s, his observation of universal expansion laid the groundwork for later discoveries. In the late 1990s, astronomers studying distant supernovae found that the expansion is accelerating, not slowing as expected. This acceleration can be understood as an effect of dark energy, which pushes space apart more strongly than gravity can pull it together, particularly in underdense regions. Voids, where gravity is weak, provide a perfect laboratory to observe the effects of dark energy more clearly, a connection that begins with Hubble's redshift measurements. Hubble's work also had philosophical and cultural implications. Before his discovery, the universe was often thought of as static and eternal, and humans might have imagined themselves as central actors on a fixed stage. Hubble revealed a dynamic, evolving cosmos filled with countless galaxies, each potentially hosting its own stars and planets. This dramatically expanded the scale of the universe, challenging humanity to reconsider its place in the cosmos. The idea that the universe is immense, expanding, and mostly empty in vast regions transformed both science and the human imagination. It is worth noting the meticulous observational work that made Hubble's discovery possible. Measuring redshifts requires extremely precise spectroscopy. Detecting Cepheid variables in distant galaxies demands powerful telescopes and careful photometry. Hubble worked at the Mount Wilson Observatory, which at the time had the world's largest optical telescope. His methodical approach, combining distance measurements with velocity data, allowed him to detect the subtle yet consistent pattern of recession among galaxies. It was not a single flash of insight, but years of careful observation, calculation, and validation that produced his groundbreaking results. Hubble's law also underpins modern cosmological models. Today, astronomers use the relationship between distance and velocity to map the large-scale structure of the universe, track the growth of cosmic voids, and measure the Hubble constant with increasing precision. Observations of redshift remain a cornerstone of cosmology, connecting galaxy motion to the expansion of space and informing our understanding of the universe's past, present, and future. Hubble's discovery teaches us about the scale and interconnectedness of cosmic forces. Expansion is not a minor phenomenon, it is a fundamental property of space itself. Gravity, while incredibly powerful locally, competes with expansion on the largest scales. The interplay of these forces shapes the distribution of matter, the growth of voids, the clustering of galaxies, and even the evolution of isolated systems. By recognizing that the universe is expanding, Hubble allowed scientists to appreciate the dynamic tension between contraction and expansion that governs the cosmos. Edwin Hubble's groundbreaking work in the late 1920s reshaped humanity's understanding of the cosmos and set the stage for modern astronomy and cosmology. Before his observations, the prevailing view of the universe was limited and largely static. Astronomers debated whether the Milky Way represented the entirety of the universe, and the motions of distant galaxies were poorly understood. Hubble, working at the Mount Wilson Observatory with the powerful Hooker telescope, changed this perspective entirely by observing distant galaxies and measuring their redshifts, the stretching of light toward longer wavelengths caused by motion away from the observer. Through meticulous observation, Hubble discovered a remarkable pattern. Almost all galaxies outside our local neighborhood were moving away from us. Even more strikingly, he found that the farther a galaxy was from Earth, the faster it appeared to recede. This relationship became known as Hubble's law, providing a precise and measurable correlation between a galaxy's distance and its recession velocity. This was not merely a statement about the motion of individual galaxies, but a revelation about the very nature of space itself. The universe was not static. It was expanding, with space stretching and carrying galaxies along like dots painted on the surface of an inflating balloon. Unlike the motion of debris flying outward from an explosion, this expansion is a stretching of the cosmic fabric, meaning galaxies move apart because the space between them grows, not because they are propelled through space in the conventional sense. Hubble's discovery had profound implications for understanding the large-scale structure of the universe. The recognition that space itself expands helped explain the formation of cosmic voids, enormous regions of near-empty space between galaxy clusters, and the way matter is distributed in filaments and superclusters. Observing the recession of galaxies also allowed astronomers to infer the universe's age and to develop the Big Bang theory, which posits that the universe originated from an extremely dense and hot initial state and has been expanding ever since. Hubble's work thus provided the first observational evidence supporting a dynamic universe rather than a static one. Beyond the immediate implications for cosmology, Hubble's findings laid the groundwork for later discoveries, including the identification of dark energy. By establishing that the universe is expanding, scientists could later measure how the rate of expansion changes over time. Observations in the late 20th century revealed that the expansion is accelerating, leading to the concept of dark energy as a dominant force shaping the cosmos. Without Hubble's initial measurements and the framework of Hubble's law, these insights would have been impossible. In essence, Edwin Hubble's work revealed a universe that is vast, evolving, and profoundly interconnected. Galaxies are not isolated islands drifting randomly through space. They are part of a dynamic, stretching cosmos governed by the interplay of matter, gravity, and the expansion of space itself. His discovery transformed our perception of the universe from a static backdrop to a living, expanding, and continuously evolving entity, opening the door to our modern understanding of cosmic evolution, structure, and the mysterious forces that drive it. Understanding the expansion of the universe can be conceptually challenging because it defies everyday intuition. Space is not simply a stage upon which galaxies move, nor is it a static container in which objects float. Instead, Space itself is dynamic, stretching and growing over time. One of the most helpful tools for visualizing this phenomenon is the balloon analogy, a simple yet powerful way to grasp the fundamental nature of cosmic expansion. Imagine a small balloon with tiny dots drawn on its surface. Each dot represents a galaxy. Initially, the balloon is deflated and the dots are relatively close together. As you blow air into the balloon, the surface stretches. The dots move away from each other, not because the dots themselves are actively moving, but because the material of the balloon, the surface itself, is expanding. The greater the distance between two dots, the faster the space between them grows. If you measure the distance between dots at regular intervals, you will notice that dots far apart separate more rapidly than dots that are close together. This is the essence of Hubble's law. The farther apart galaxies are, the faster they recede. This analogy clarifies a crucial point. Galaxies are not being flung through pre-existing space like cannonballs or debris. The expansion occurs in the very fabric of space itself. Each galaxy remains embedded in its local region of space, moving only minimally relative to nearby galaxies, but as space stretches, the distance between galaxies increases. This stretching is uniform across the cosmos, affecting all regions similarly. The balloon analogy allows us to intuitively grasp how expansion can produce enormous separations between galaxies without requiring them to accelerate individually. Another important feature of the analogy is that it illustrates the concept of relative motion. Every dot on the balloon observes the same phenomenon. The other dots are moving away. There is no central point from which everything expands. Expansion happens everywhere. Similarly, in the universe, there is no center of expansion. Every galaxy sees other galaxies receding, and the farther a galaxy is, the faster it appears to recede. This uniformity is a fundamental property of space, reflecting the cosmological principle that the universe is homogeneous and isotropic on large scales. While the balloon analogy is a simplification, it represents the universe in two dimensions, whereas actual space is three-dimensional. It captures the key ideas of cosmic expansion. It demonstrates that distances increase over time, that recession is due to space itself stretching, and that the apparent velocity of galaxies depends on separation. It also helps explain how large-scale structures and empty regions known as cosmic voids emerge naturally as a result of this process. Consider a region of the balloon with fewer dots. As the balloon expands, the space in this underpopulated region stretches more visibly than areas densely packed with dots. Similarly, in the universe, areas with fewer galaxies experience less gravitational resistance to expansion. Gravity works like a cosmic glue, holding together stars, galaxies, and clusters of galaxies. In dense regions, this pull can partially resist the stretching of space. But in regions that are already under sense, gravity is weak and expansion dominates. Over billions of years, these low-density regions grow even emptier, forming vast cosmic voids that can span hundreds of millions of light-years. The Boötes Void is a prime example of this process. It is one of the largest known voids in the universe, roughly 330 million light-years across. Like an empty patch on the balloon's surface, it represents a region where few galaxies exist and where the stretching of space has pushed matter farther apart over eons. By comparing the Boötes Void with denser regions, astronomers can study the interplay between gravity and expansion. Dense filaments of galaxies act as tension points in the cosmic web, while voids expand and grow in the opposite direction, shaping the universe's sponge-like structure. The balloon analogy also highlights how observers perceive recession. From the perspective of a single galaxy within the universe, other galaxies appear to move away. However, this motion is not due to any propulsive force acting on the galaxies themselves, but is a direct consequence of the expansion of space. If observers were situated on a galaxy within a void, they would see the few galaxies in their vicinity moving away, with more distant galaxies receding even faster. This would reinforce the perception of isolation, emphasizing the emptiness of the cosmic landscape. Furthermore, the analogy explains why expansion affects distant galaxies more dramatically than nearby ones. On small scales, local gravitational forces dominate. Planets remain bound to stars, stars to galaxies, and galaxies within clusters remain gravitationally linked. The expansion of space is effectively negligible at these scales. It is only across immense cosmic distances, hundreds of millions to billions of light-years, that expansion becomes the dominant factor, stretching space and increasing the separation between objects that are only weakly bound gravitationally. The stretching of space also impacts the observable universe. Light traveling from distant galaxies is stretched along with space, leading to the phenomenon of redshift. This is analogous to marking a rubber band with a series of lines. As the band is stretched, the lines move farther apart. In cosmology, this stretching of light allows astronomers to measure the expansion rate of the universe, estimate distances, and map the distribution of galaxies across cosmic time. Beyond its explanatory power for expansion, the balloon analogy provides insight into the evolution of cosmic voids and the large-scale structure of the universe. Imagine the balloon surface with a mix of densely packed dots and sparse regions. As it inflates, dense clusters of dots remain relatively close due to local cohesion, while sparse regions stretch more, becoming emptier. Over billions of years, the universe's initial slight density variations are amplified. Dense regions grow denser, forming filaments and clusters, while underdense regions expand and empty out, creating the voids. This process naturally produces the cosmic web, a network of filaments, clusters, and voids that we observe today. Cosmic voids, while seemingly empty, are not entirely devoid of matter. A few isolated galaxies may exist, floating like tiny islands within vast oceans of emptiness. Studying these isolated galaxies is crucial because they offer a laboratory to observe galaxy evolution in minimal interaction environments. Unlike galaxies in crowded clusters, which frequently collide, merge, and exchange matter, void galaxies evolve largely in isolation. Their unique properties provide insight into fundamental processes of star formation, galaxy growth, and the role of environment in shaping cosmic structures. The balloon analogy also illustrates why cosmic expansion is not uniform in its effect on different structures. In areas of high density, such as galaxy clusters, gravity counteracts expansion, slowing it down locally. In contrast, in the nearly empty voids, the expansion proceeds unimpeded. This differential effect explains why the universe is structured with both dense filaments and enormous voids. Expansion stretches the cosmic web and accentuates existing density contrasts, reinforcing the patterns we see on the largest scales. Another consequence of cosmic expansion, highlighted by the balloon analogy, is the gradual isolation of galaxies. Over billions of years, galaxies not gravitationally bound to clusters or superclusters will recede beyond observable distances. For a hypothetical civilization within a galaxy in a void, the sky would appear increasingly empty. Other galaxies would fade and disappear from view, emphasizing the vast loneliness of such cosmic regions. Observers would eventually witness only their own galaxy and a few nearby companions, isolated in a dark, ever-expanding void. The analogy also aids in understanding the influence of dark energy on cosmic expansion. While the balloon analogy represents uniform stretching, in reality, the universe's expansion is accelerating due to dark energy. In voids, where gravity is weak, dark energy exerts its full effect, accelerating the separation of galaxies and enlarging these underdense regions. By studying voids like Boötes, astronomers can gain a clearer picture of dark energy's properties and influence, as these regions are less affected by gravitational interference from nearby dense structures. The balloon analogy encourages a shift in perspective. It invites us to view the universe not as a static backdrop, but as a living, evolving entity. Every galaxy, cluster, filament, and void is part of a dynamic cosmic dance. The large-scale emptiness of voids, the intricate connectivity of the cosmic web, and the relentless expansion of space itself are all consequences of this interplay. The analogy helps us internalize the notion that space is not merely a passive arena, but an active participant in shaping the universe's structure. The balloon analogy provides a powerful mental model for understanding cosmic expansion. It illustrates how galaxies move with space rather than through it, how distances grow faster with increasing separation, and how underdense regions expand more rapidly, forming cosmic voids. It clarifies the relationship between local gravitationally bound systems and large-scale expansion, and it offers insight into the observable consequences of this expansion, including redshift and the evolving cosmic web. By imagining the universe as a stretching balloon, we gain a clearer grasp of the dynamic nature of space, the growth of emptiness, and the intricate structure of the cosmos on the grandest scales. The universe is governed by a delicate interplay of forces acting across vastly different scales. On one hand, we have gravity, the force that binds stars, planets, galaxies, and clusters together. On the other hand, there is the expansion of space itself, an effect that becomes increasingly significant as we look across the immense distances separating galaxy clusters and superclusters. To understand the formation of cosmic structures, particularly the enormous voids and filaments that define the cosmic web, it is essential to examine how these forces dominate at different scales, how they interact, and how their interplay shapes the universe we observe today. On small scales, gravity is overwhelmingly dominant. Within a solar system, for instance, the gravitational pull of a star keeps its planets in stable orbits. The Earth, bound tightly to the Sun, follows an elliptical orbit, never drifting into empty space, despite the universe's continuous expansion. The same principle applies on slightly larger scales. The Sun itself remains gravitationally bound to the Milky Way galaxy. Billions of stars in our galaxy orbit the central supermassive black hole and move within the galactic disk, all held together by gravity's persistent pull. Even on the scale of galaxy pairs or small galaxy groups, such as the Milky Way and Andromeda, gravity maintains cohesion. Though Andromeda is moving toward the Milky Way at hundreds of kilometers per second, it is not a random motion through space. It is driven by the mutual gravitational attraction of these massive galaxies. This dominance of gravity at small scales ensures the stability of local systems. Planets, stars, and galaxies remain intact, unaffected by the large-scale expansion of space. The effects of cosmic expansion are negligible when gravity is strong, because gravitational attraction counteracts the subtle stretching of space. Within galaxy clusters, where hundreds or thousands of galaxies are tightly packed, gravity continues to hold these systems together, resisting the universe's expansion. Even galaxy groups that are tens of millions of light-years across remain cohesive due to gravitational binding, forming local islands of structure amidst the larger-scale growth of the universe. However, as we move to much larger scales, gravity's influence diminishes. Beyond the scale of individual clusters or superclusters, the gravitational pull between structures weakens with distance. The universe is not uniform in density. There are dense areas where galaxies are clustered, and underdense areas where galaxies are sparse or nearly absent. In these low-density regions, gravity cannot compete with the expansion of space. Over distances of hundreds of millions to billions of light-years, the pull of gravity becomes too weak to keep matter tightly bound. It is in these enormous stretches of space that the effects of expansion dominate, stretching the fabric of the cosmos and pulling distant galaxies apart. This scale-dependent behavior of forces explains the contrasting structure of the universe. Dense regions of the cosmos, where gravity is strong, become the glowing filaments of the cosmic web. Here, galaxies cluster together along long, thread-like structures, forming a network that connects galaxy clusters and superclusters across the universe. The filaments are visible as linear arrangements of galaxies, stretching for hundreds of millions of light-years. Gravity's pull ensures that matter remains concentrated in these regions, giving rise to the bright, interconnected structures that define the large-scale architecture of the universe. In contrast, the low-density regions between these filaments evolve into vast cosmic voids. In voids, the scarcity of matter means that gravitational pull is minimal. Space is free to expand without resistance, and over billions of years, this expansion stretches these regions, making them even emptier. The result is a universe organized like a sponge, with dense filaments and clusters separated by enormous empty spaces. The Boötes Void, one of the largest known voids, illustrates this principle spectacularly. Spanning roughly 330 million light-years, it contains only a few isolated galaxies, emphasizing the dominance of expansion over gravity in shaping such regions. This interplay between local gravitational dominance and large-scale expansion also helps explain how matter is distributed in the universe. Initially, after the Big Bang, matter was distributed almost uniformly, with slight density fluctuations. In denser regions, gravity amplified these fluctuations, drawing more matter inward and forming galaxies and clusters. In underdense regions, the lack of matter meant that expansion proceeded unchecked, enlarging the empty spaces. Over billions of years, these processes produced the cosmic web, a vast, interconnected pattern of filaments, nodes, and voids that defines the universe's large-scale structure. Observing local versus large-scale forces is critical for understanding the dynamics of the universe. On small scales, phenomena such as star formation, galaxy mergers, and orbital mechanics are dominated by gravity. In contrast, the expansion of space shapes the universe on scales far beyond clusters of galaxies, influencing the formation of voids and the separation of cosmic structures. The two forces are not mutually exclusive. They coexist and interact, creating the intricate pattern of dense and empty regions that astronomers observe today. Cosmic voids, in particular, offer a unique laboratory to study the effects of expansion. Because these regions are underdense, the influence of gravity is weak, allowing the expansion of space to be observed more clearly. By measuring how voids grow over time and how the few galaxies within them move, scientists can gain insights into the behavior of dark energy, the mysterious force driving the universe's accelerated expansion. The contrast between gravity-dominated filaments and expansion-dominated voids highlights the importance of scale in cosmic physics. The concept of scale-dependent forces explains the apparent motion of galaxies. Nearby galaxies, bound by gravity, move together in coherent structures, while distant galaxies recede due to the expansion of space. From any given galaxy, observers perceive that other galaxies are moving away, with the speed of recession increasing with distance. This perception is not caused by motion through space, but by the stretching of space itself, a distinction that is crucial for understanding the universe's large-scale behavior. In the context of galaxy evolution, the separation of forces also has profound implications. Galaxies in dense clusters are subject to frequent interactions, collisions, and mergers, which can trigger star formation and alter their morphology. Galaxies in voids, by contrast, evolve in isolation, with little external influence. Studying galaxies in both environments allows astronomers to disentangle the effects of local gravitational interactions from the broader impact of cosmic expansion. Furthermore, the differential influence of gravity and expansion shapes the future of the universe. Over billions of years, regions not gravitationally bound will continue to recede, eventually moving beyond the observable horizon. Filaments and clusters will remain coherent due to gravity, but the spaces between them will grow ever emptier. This ongoing separation is a direct consequence of the large-scale dominance of expansion over gravity in low-density regions. The balance between local gravitational forces and large-scale expansion also informs our understanding of the universe's age and evolution. By observing the distribution of galaxies, filaments, and voids, astronomers can reconstruct the history of cosmic expansion and test models of structure formation. Voids, in particular, provide a sensitive measure of the expansion rate because they respond more directly to the stretching of space than dense regions, where gravity partially counteracts expansion. In essence, the universe's structure is a manifestation of the tug-of-war between gravity and expansion. On small scales, gravity rules, holding stars, galaxies, and clusters together in stable configurations. On larger scales, expansion dominates, separating structures and enlarging voids. This interplay produces the strikingly complex and beautiful cosmic web, a pattern of dense filaments intertwined with vast emptiness, spanning billions of light-years. Understanding local versus large-scale forces also has practical implications for astronomy. When measuring distances, redshifts, and the motions of galaxies, astronomers must account for both gravitationally bound motion and expansion-driven recession. The velocity of a galaxy relative to its local cluster may differ from its velocity due to the expansion of the universe, and disentangling these contributions is essential for accurate cosmological measurements. Recognizing the scale-dependent dominance of forces enhances our appreciation of the universe's dynamic nature. Gravity shapes the familiar structures we can observe up close, from solar systems to galaxy clusters. Expansion shapes the universe at the grandest scales, stretching space, forming voids, and driving the accelerated growth of cosmic separations. Together, these forces create a universe that is both structured and ever-changing, a cosmos where dense islands of matter float in vast seas of emptiness, each scale governed by the appropriate force. The contrast between local and large-scale forces provides a framework for understanding the formation and evolution of the universe. Gravity dominates at small scales, ensuring the cohesion of planets, stars, galaxies, and clusters. At very large scales, expansion takes over, stretching the fabric of space and creating vast voids between clusters and filaments. The interplay between these forces explains the universe's striking sponge-like structure and allows scientists to study both the visible and invisible components of the cosmos. By observing how structures respond to these competing influences, we gain insight into the underlying physics of the universe, including the role of dark energy in shaping the future of cosmic expansion. Cosmic voids are among the most fascinating and enigmatic structures in the universe. Though they might appear as mere empty regions, they are dynamic, evolving, and fundamental to understanding the cosmos at its largest scales. Voids are not simply leftover gaps between galaxies or clusters. They are active regions shaped by the expansion of space, gravity, and the initial conditions of the universe itself. Their growth over billions of years provides astronomers with a unique laboratory to study cosmic evolution, the influence of dark energy, and the very fabric of space-time. To visualize the growth of voids, consider a simple analogy. Imagine a web made of elastic bands with marbles stuck at the intersections. The marbles represent galaxies or galaxy clusters, and the rubber web represents the cosmic fabric of space. As the web is stretched, the marbles remain relatively close to each other because they are bound together by the strength of gravity. However, the spaces between the marbles, particularly those regions with few or no marbles to begin with, stretch dramatically. Over time, these empty spaces grow, becoming larger and more isolated. In the universe, this analogy translates directly to voids. Regions of space that were initially underdense in matter continue to lose material as gravity pulls matter toward denser regions. The result is that these already sparse regions expand, forming the enormous cosmic voids observed today. The Boötes Void exemplifies this process. Discovered in 1981, it is one of the largest known voids in the observable universe, spanning approximately 330 million light-years. Despite its massive scale, it contains only a few isolated galaxies, emphasizing its extreme emptiness. The Boötes Void did not simply appear fully formed, it grew gradually over billions of years. Initially, after the Big Bang, tiny fluctuations in the density of matter existed throughout the cosmos. Regions that were slightly denser attracted more matter through gravity, forming the seeds of galaxies, clusters, and filaments. Conversely, regions that were slightly less dense, the precursors to voids, contained less matter. Gravity then acted to pull material away from these underdense regions toward the denser filaments, amplifying their emptiness. As the universe expanded, these underdense regions became more pronounced. Unlike dense filaments where gravity resisted expansion, voids experienced little opposition. The stretching of space caused voids to grow in size, making the few galaxies within them drift even farther apart. Over cosmic time, this process transformed what may have been modest underdense regions into the massive, hauntingly empty expanses we now identify as cosmic voids. The Boötes Void, due to its scale and extreme isolation, illustrates this effect on an extraordinary level, providing astronomers with a remarkable example of how emptiness evolves in a dynamic universe. The growth of voids is not uniform. While some voids expand steadily, others interact with neighboring voids, merging to form even larger empty regions. These mergers occur because voids are not isolated entities. They are part of a vast, interconnected cosmic web. When two underdense regions lie adjacent to each other, the space between them stretches, gradually connecting the two voids into a single, more extensive void. This process can create tunnel-like structures or cavernous empty regions stretching hundreds of millions of light-years. Such phenomena reveal the dynamic and evolving nature of voids. They are not static gaps, but living components of the universe's large-scale architecture. The expansion-driven growth of voids also has profound implications for the galaxies that reside within them. Galaxies inside voids are isolated and experience minimal gravitational interaction with neighbors. Unlike galaxies in dense clusters, they do not frequently collide or merge. This isolation leads to unique evolutionary paths. Star formation may proceed more slowly or steadily, undisturbed by external disruptions. Galactic morphology can differ, with fewer signs of tidal distortions or chaotic mergers. In essence, void galaxies evolve in a cosmic laboratory that allows scientists to study how galaxies develop when stripped of the complex influences present in denser environments. Furthermore, voids provide essential insights into dark energy, the mysterious force accelerating the universe's expansion. In regions of low matter density, like voids, gravitational forces are weak, allowing the influence of dark energy to dominate. As a result, voids are stretched outward more efficiently than dense regions, offering astronomers a natural environment to study the effects of dark energy in relative isolation. By measuring how voids expand over time and how galaxies within them respond, scientists can refine models of cosmic acceleration and gain a clearer understanding of the fundamental forces shaping the universe. The dynamics of void growth also reveal the interplay between local and large-scale structures. Dense regions where gravity dominates become filaments and clusters, while low-density regions grow into voids. This contrasting evolution contributes to the striking sponge-like pattern of the cosmic web. Observing the sizes, shapes, and distribution of voids across the universe allows astronomers to reconstruct the history of cosmic expansion, offering clues about the initial conditions following the Big Bang and the forces that have driven the evolution of large-scale structure. Interestingly, voids are not perfectly empty. They contain small amounts of matter, including dark matter, which influences their growth subtly. The tiny gravitational pull from this sparse matter can shape the void's internal structure, slightly affecting the motion of isolated galaxies. Dark energy, meanwhile, acts uniformly throughout the void, ensuring that the expansion remains accelerated and consistent with observations. These combined effects make voids highly informative regions, helping cosmologists distinguish the influence of gravity from the influence of dark energy. Over billions of years, the growth of voids leads to a progressively emptier universe. As space expands, galaxies outside voids drift farther apart, and the voids themselves enlarge. The Boötes Void, for example, continues to expand every moment, its emptiness deepening over time. Looking into the future, this process implies that the universe will become increasingly dominated by isolated pockets of matter, surrounded by vast empty spaces. Clusters and filaments may remain bound locally, but the voids will grow larger and lonelier, shaping the ultimate fate of cosmic structures. The study of voids also has profound implications for our understanding of cosmic history. By examining how voids evolve and interact with their surroundings, astronomers can infer the distribution of matter in the early universe. Tiny fluctuations in density, amplified over billions of years by gravitational dynamics and cosmic expansion, explain the emergence of the universe's filamentary and void-rich structure. Each void, whether enormous like the Boötes Void or smaller, provides a snapshot of the universe's growth and a test of cosmological models. Cosmic voids further illuminate the connection between the visible and invisible universe. While the galaxies we observe are luminous, much of the universe's mass is dark matter, detectable only through its gravitational effects. Voids, by their nature, contain less dark matter than denser regions, but the distribution of this dark matter within voids influences their shape and expansion. Studying voids therefore helps scientists map both the luminous and dark components of the universe, offering a more complete picture of cosmic structure. In addition, voids affect the movement of nearby galaxies. A galaxy near a void experiences less gravitational pull in the direction of the void, causing it to move slightly away from the emptiness toward denser regions. This phenomenon contributes to the peculiar velocities of galaxies, deviations from the motion expected solely from cosmic expansion. Understanding these motions helps astronomers map the three-dimensional structure of the universe and the distribution of matter on large scales. Void evolution also interacts with cosmic radiation. The cosmic microwave background, CMB, the afterglow of the Big Bang, can be influenced by voids through effects like the integrated Sachs-Wolf effect. Light passing through an expanding void can gain or lose energy, leading to subtle temperature fluctuations in the CMB. Studying these interactions provides additional constraints on the growth of voids, the nature of dark energy, and the overall evolution of the universe. The Boötes Void and other large voids remind us that emptiness is an integral part of the cosmic design. Without voids, the cosmic web would not exhibit its filamentary sponge-like structure. The contrast between dense glowing filaments and vast empty voids gives the universe its large-scale texture, influences galaxy evolution, and allows scientists to probe fundamental forces in regions relatively free from interference. Cosmic voids are not mere absences of matter. They are dynamic, expanding, and informative structures that reveal the universe's evolution, the influence of dark energy, and the distribution of matter. They grow because of the stretching of space and the relative weakness of gravity within them, forming enormous regions like the Boötes Void. Their study provides insights into galaxy evolution, cosmic history, dark energy, and the interplay of forces across scales. As the universe ages, voids will continue to grow, becoming larger and lonelier, yet remaining critical components in the grand tapestry of cosmic structure. They embody the principle that even emptiness has purpose, actively shaping the universe while offering a window into its most profound mysteries. For most of the 20th century, astronomers believed that the expansion of the universe, first discovered by Edwin Hubble in the 1920s, was slowing down. Gravity, the attractive force that pulls matter together, was assumed to be the dominant influence on cosmic scales. As matter clumped into stars, galaxies, and clusters, it exerted a gravitational pull that resisted the stretching of space. Scientists expected that this pull would gradually decelerate the expansion of the universe, possibly even leading to a future contraction in a scenario known as the Big Crunch. For billions of years, this was the prevailing assumption in cosmology. The universe was expanding, but the rate of expansion should slowly decrease as gravitational forces worked to pull matter together. However, the late 1990s brought a surprising and revolutionary discovery. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were studying distant supernovae to better understand the history of cosmic expansion. Supernovae are massive stellar explosions that can outshine entire galaxies for a short period, and certain types, called Type 1a supernovae, serve as standard candles because their intrinsic brightness is well understood. By comparing the apparent brightness of these explosions to their known intrinsic brightness, astronomers can calculate their distance from Earth. Additionally, by measuring the redshift of the light, scientists can determine how fast these supernovae are moving away from us. When the teams analyzed the supernova data, they expected to see distant supernova slightly brighter than anticipated under a decelerating universe model, which would indicate a slower expansion in the past. Instead, the results shocked the scientific community. The supernovae appeared dimmer than expected. Dimmer supernovae meant that they were farther away than predicted, implying that the universe's expansion was not slowing down, it was accelerating. This was a completely unexpected result and required a radical rethinking of cosmology. To explain this acceleration, scientists proposed the existence of a mysterious, pervasive force or energy embedded within space itself. This force, which seemed to counteract gravity and push space apart, was termed dark energy. Dark energy is unlike any conventional matter or energy we experience in daily life. It does not clump like normal matter, does not emit light, and cannot be detected directly through electromagnetic signals. Yet, its influence is profound. It dominates the dynamics of the universe on the largest scales, driving galaxies apart and stretching cosmic voids. Today, dark energy is estimated to make up about 68% of the total energy content of the universe, dwarfing both normal matter, about 5%, and dark matter, about 27%. The discovery of dark energy marked one of the most significant paradigm shifts in modern cosmology. Prior to this, gravity was thought to be the dominant force governing the universe's large-scale behavior. But in the vast, underdense regions like cosmic voids, gravity is relatively weak, and the influence of dark energy becomes overwhelmingly apparent. The universe is not merely expanding, it is accelerating, and the emptiest regions expand faster than the denser areas. Cosmic voids therefore serve as natural laboratories to observe the effects of dark energy with minimal interference from gravity. Dark energy acts somewhat like anti-gravity, pushing space apart rather than pulling matter together. Unlike gravity, which diminishes with distance, dark energy appears to act uniformly across the universe, independent of local matter density. This uniformity ensures that even in regions where galaxies are tightly clustered, dark energy still exerts a small push, though its effects are most noticeable in empty spaces. In cosmic voids, where matter is sparse and gravity is weak, dark energy dominates completely, accelerating the expansion of space and making voids grow even emptier. The concept of dark energy also reshaped our understanding of the universe's past and future. If expansion is accelerating, then the universe is not headed toward a collapse under gravity, as previously hypothesized. Instead, the acceleration suggests a future in which galaxies continue moving apart at increasing speeds, eventually becoming isolated in vast, empty regions. The very structure of the universe, including filaments, clusters, and voids, will be stretched and transformed by the relentless push of dark energy. Over tens of billions of years, galaxies not gravitationally bound to one another will disappear from each other's view, leaving each galaxy or cluster effectively alone in the expanding cosmos. Astronomers and physicists have explored various models to explain the nature of dark energy. One possibility is the cosmological constant, originally proposed by Albert Einstein in 1917 as a term in his equations of general relativity. Einstein introduced this constant to allow for a static universe, which he later abandoned after Hubble's discovery of cosmic expansion. However, the cosmological constant has regained relevance as a simple model for dark energy. It represents a constant energy density per unit volume of space, providing a repulsive force that drives acceleration. Other theories suggest dynamic forms of dark energy, often called quintessence, which might change in intensity over time or vary across regions of the universe. Observing voids and measuring their expansion can help distinguish between these models, as the behavior of empty regions is sensitive to the properties of dark energy. The discovery of dark energy also sparked a surge of observational programs and theoretical research. Large-scale surveys of galaxies, precise measurements of the cosmic microwave background, CMB, and detailed studies of supernovae all contribute to mapping how the universe is expanding and how dark energy influences cosmic structures. Voids, particularly enormous ones like the Boötes Void, play a crucial role in this research because they provide relatively clean environments where the effects of dark energy are not masked by complex gravitational interactions. Tracking the growth of voids over time allows scientists to test the predictions of different dark energy models and refine our understanding of the universe's accelerating expansion. Beyond the purely scientific implications, the discovery of dark energy challenges our philosophical and existential perspectives. For billions of years, life and matter have evolved in a universe whose large-scale structure is shaped not only by visible galaxies and dark matter, but by this invisible, mysterious force that dominates space itself. Dark energy reminds us that the universe is far stranger than previously imagined. It is not simply matter moving through space, but a dynamic, expanding fabric in which most of the energy content is invisible and largely unknown. The emptiest regions, once thought to be voids with little importance, are now recognized as key laboratories for understanding the universe's ultimate fate. In addition, the interplay of dark energy with cosmic voids highlights how isolation and emptiness are central to cosmic evolution. In the emptiest corners of the universe, the acceleration of space becomes most pronounced. The few galaxies within voids are carried apart with increasing speed, and any signs of past interactions are stretched beyond recognition. These isolated regions provide insight into a universe dominated by dark energy, offering a glimpse of the distant future when cosmic structures are separated by ever-expanding voids. In essence, the discovery of dark energy transformed our understanding of the universe from a picture dominated by gravitational forces to one where a mysterious, repulsive energy shapes the ultimate destiny of cosmic structures. By accelerating the expansion of space, dark energy drives the growth of voids, isolates galaxies, and dictates the large-scale structure of the cosmos. Observations of voids, supernovae, and the CMB continue to refine our understanding, providing both empirical evidence and theoretical challenges. While the nature of dark energy remains one of the deepest mysteries of modern physics, its discovery has fundamentally changed how we perceive the universe, revealing that the emptiest regions of space are as crucial to cosmic evolution as the densest. The late 1990s observations of distant supernovae not only uncovered this invisible force, but also emphasized the importance of precision astronomy, patience, and careful measurement in uncovering the hidden mechanisms of the cosmos. By studying how galaxies, clusters, and voids behave under the influence of dark energy, scientists continue to unravel the story of the universe's expansion, its past, and its future. Today, cosmologists are leveraging the growth and dynamics of voids to answer key questions. How does dark energy vary across time and space? Will the universe expand forever, or will dark energy evolve in ways we cannot yet predict? Can voids provide constraints on competing theories of cosmology? Each void, each isolated galaxy, and each stretching filament contributes to a broader understanding of dark energy and the accelerating cosmos. The discovery of dark energy revolutionized our view of the universe. It revealed that the universe is not just expanding but accelerating, driven by a mysterious force that acts like anti-gravity. Cosmic voids, especially enormous ones like the Boötes Void, are natural laboratories where the influence of dark energy is most apparent. They provide insights into the evolution of cosmic structures, the behavior of galaxies in isolation, and the ultimate fate of the universe. The study of dark energy continues to be at the forefront of modern astronomy and physics, pushing our understanding of the cosmos into realms that were unimaginable just a few decades ago. Dark energy is one of the most profound and mysterious aspects of the cosmos. Unlike ordinary matter, which clumps together under the influence of gravity, or dark matter, which exerts gravitational effects but remains invisible, dark energy behaves very differently. It appears to be a property of space itself, a force or energy that is present uniformly throughout the universe. Whether one is looking at a dense cluster of galaxies or the near-empty depths of a cosmic void, dark energy is thought to exert a constant push, resisting the natural clumping effects of gravity and accelerating the expansion of space. On large cosmic scales, the universe is a complex interplay between gravity and dark energy. Gravity, arising from all forms of matter, including ordinary and dark matter, pulls material together, forming galaxies, clusters, and even superclusters. In contrast, dark energy operates as a repulsive force, pushing space apart and driving galaxies farther from each other. The balance of these forces varies depending on the density of the region in question. In dense areas such as galaxy clusters, the gravitational pull is strong and the effects of dark energy are largely masked. Gravity can hold galaxies together over billions of light years, overcoming the repulsive push of dark energy locally. In these regions, expansion occurs more slowly and the clustering of matter dominates the structure of the universe. In stark contrast, cosmic voids are the natural laboratories for observing dark energy. Voids are enormous regions of space where matter is extremely sparse. These regions often contain very few galaxies and almost no clusters, making them among the emptiest areas in the observable universe. Because gravity in voids is weak, there is little to counteract the influence of dark energy. The result is that expansion dominates entirely in these regions, pushing the sparse galaxies apart at an accelerated rate. As a consequence, voids grow faster than the denser filaments, clusters and superclusters, stretching and becoming more empty with time. The uniform nature of dark energy ensures that its effect is the same everywhere, independent of local matter density. This uniformity means that, unlike gravity, dark energy does not favor any particular location. Its influence is subtle in dense clusters, where it is largely countered by gravitational attraction, but in underdense voids, dark energy's impact is immediate and obvious. Observing the growth of these voids provides critical clues about the behavior of dark energy and how it shapes the universe. Because voids are relatively clean environments, free from strong gravitational interference, scientists can study the expansion of space more directly than in crowded regions of the cosmos. The process of void growth is continuous and dynamic. Even within a single void, galaxies that exist are slowly drifting away from each other as the fabric of space stretches. This expansion is not uniform on smaller scales. Local gravitational interactions can still slightly influence galaxy motion, but on the scale of tens to hundreds of millions of light years, dark energy dominates entirely. Over time, the void becomes larger, lonelier, and increasingly desolate. Some voids span hundreds of millions of light years, containing only a handful of isolated galaxies in their immense interior. The emptiest voids, like the Boötes Void, serve as extreme examples of how dark energy shapes cosmic structure. Studying voids has given scientists a powerful tool to probe the nature of dark energy. By mapping the distribution of galaxies within voids, measuring how rapidly the distances between them increase, and tracking the shape and growth of the void itself, astronomers can infer properties of dark energy with remarkable precision. The relative simplicity of voids, compared to the crowded and complex interactions in galaxy clusters, allows for cleaner measurements and more accurate modeling of cosmic expansion. Scientists compare observations of voids with theoretical predictions to test whether dark energy behaves as a constant cosmological term, as Einstein originally suggested, or whether it changes over time, as some dynamic models propose. The effect of dark energy on voids also provides insight into the future of the universe. As expansion continues and accelerates, voids will keep growing, gradually isolating the galaxies that lie within them. Over billions of years, the separation between galaxies in voids will increase so much that they will become virtually unreachable from one another. Light from neighboring galaxies may become stretched beyond detection, effectively rendering each galaxy a solitary island in the vast cosmic ocean. This isolation underscores the long-term consequences of dark energy. The universe will evolve toward an ever lonelier and emptier state, with the largest voids becoming more prominent features of the cosmic landscape. One striking aspect of dark energy in voids is how it emphasizes the scale-dependent nature of cosmic forces. In regions with high matter density, such as the cores of galaxy clusters, gravity overwhelms dark energy, binding galaxies together and maintaining structural cohesion. But in underdense voids, where matter is scarce and gravitational forces are minimal, dark energy dominates completely. This dichotomy highlights the duality of cosmic dynamics. The same universe that can hold galaxies tightly in clusters also permits vast, accelerating emptiness elsewhere. Understanding this balance is essential for constructing accurate models of cosmic evolution. Astronomers also use computer simulations to study void growth and the influence of dark energy. By creating virtual universes in which the properties of dark energy can be varied, scientists can predict how voids should evolve over time. Observations of real cosmic voids are then compared against these models. If the observed voids grow differently than predicted, it may indicate that our understanding of dark energy is incomplete. Conversely, if observations match the simulations, it provides strong evidence that current models of dark energy are accurate. In addition to studying the large-scale expansion, voids also provide insight into the behavior of individual galaxies in isolation. Galaxies within voids often show different properties from those in clusters or filaments. They may experience slower rates of star formation due to the lack of nearby interactions or mergers, or they may evolve differently because of reduced exposure to cosmic radiation from surrounding matter. The emptiness of their environment makes void galaxies natural laboratories for studying how local and global cosmic forces interact. Dark energy, by expanding the space around these galaxies, fundamentally shapes their evolution over cosmic time. The uniform distribution of dark energy also raises questions about its origin and nature. Unlike matter, which can be traced to specific particles and interactions, dark energy is pervasive and seemingly intrinsic to space itself. Some theories propose that it is a manifestation of vacuum energy, the energy inherent in empty space at the quantum level. Others suggest more exotic explanations, such as modifications to the laws of gravity or the existence of a dynamic field permeating the universe. Regardless of its origin, the clear influence of dark energy in voids provides one of the most direct ways to measure and understand it. Dark energy also interacts with the concept of the cosmic web. The universe on the largest scales is structured like a vast web, with galaxies and clusters forming dense filaments and nodes, while voids occupy the spaces in between. The filaments are held together primarily by gravity, while the voids expand under the influence of dark energy. This dynamic interplay leads to a constantly evolving cosmic architecture. Dense regions remain relatively coherent, while the emptiest regions stretch and grow, increasing the contrast between clusters and voids over time. Observing these changes allows scientists to test predictions of cosmic structure formation and to measure the relative strength of dark energy. In essence, dark energy is the engine driving the growth of cosmic voids. Its uniform presence, combined with the relative weakness of gravity in undersense regions, ensures that voids expand faster than the rest of the universe. These empty regions not only reveal the nature of dark energy, but also provide a window into the long-term evolution of the cosmos. By studying voids, astronomers can refine their understanding of the universe's expansion, test theoretical models, and predict the ultimate fate of galaxies trapped within these vast accelerating spaces. Cosmic voids are far from being mere empty spaces. They are dynamic, evolving regions shaped primarily by dark energy. The emptiness of voids amplifies the effects of this mysterious force, allowing scientists to observe cosmic acceleration in its clearest form. As voids continue to expand, they offer unique opportunities to study both the present behavior and the future consequences of dark energy. By examining voids, mapping their growth, and observing the galaxies within them, astronomers can gain critical insight into the most fundamental and least understood force shaping our universe. The study of dark energy in voids continues to be one of the central challenges and most exciting frontiers of modern cosmology. The Boötes Void is one of the most fascinating and mysterious structures in the observable universe. Spanning an immense distance of roughly 330 million light-years across, it is not just a large cosmic feature. It is a symbol of emptiness on a scale that challenges human imagination. Often referred to as the Great Nothing, this void is striking both for its sheer size and for the extreme paucity of galaxies within it. While most regions of the universe teem with hundreds or even thousands of galaxies, the Boötes Void contains only a few dozen, making it one of the loneliest places in the cosmos. Its extreme underdensity and vast spatial scale make it an invaluable natural laboratory for the study of fundamental cosmological phenomena, especially dark energy and the large-scale structure of the universe. To understand why the Boötes Void is such a critical laboratory, it is essential first to grasp what a cosmic void is. Voids are enormous regions of space where matter is extremely sparse, sometimes containing only isolated galaxies or small groups. They are not anomalies or mistakes in cosmic surveys, rather they are natural outcomes of the universe's evolution. Gravity tends to pull matter together, forming clusters and filaments, while regions with initially lower density are left behind. These low-density regions are stretched even further by the expansion of the universe, especially under the influence of dark energy, which acts as a repulsive force pushing space apart. The Boötes Void represents an extreme example of this process. While ordinary voids can be tens of millions of light-years across, the Boötes Void extends over 300 million light-years in diameter. To put this in perspective, our Milky Way galaxy is only about 100,000 light-years across. This means that the Boötes Void is more than 3,000 times wider than our own galaxy, creating a vast emptiness where galaxies are scattered like isolated specks in a sea of darkness. The enormity of this void provides a unique environment in which the effects of dark energy can be studied without the complicating influence of nearby massive structures. In dense regions of the universe, the gravitational pull of surrounding galaxies can mask or distort the effects of dark energy, making it harder to observe and measure. But inside a vast emptiness like the Boötes Void, gravity is weak, and the repulsive effects of dark energy dominate the motion of galaxies. By carefully observing the galaxies that do exist within the Boötes Void, scientists can track how the void itself is expanding over time. Galaxies that start relatively close to one another drift apart as the space between them stretches. Measuring these changes allows astronomers to estimate the rate at which dark energy is pushing the universe apart. If dark energy is truly a constant property of space, its effects on void expansion should be predictable. The rate at which galaxies within the Boötes Void move away from one another should match theoretical models based on a uniform dark energy density. On the other hand, if dark energy varies over time or behaves differently in different regions, the growth pattern of the Boötes Void would deviate from these predictions. Observing such deviations could reveal new physics beyond the current understanding of the universe. The sheer size of the Boötes Void also provides a statistical advantage for studying cosmic expansion. In smaller voids or less empty regions, random fluctuations in galaxy distribution or local gravitational effects can complicate measurements. But in a void as vast as Boötes, these random effects are minimized. The dynamics of galaxy motion are largely governed by the large-scale expansion of space itself, providing a cleaner environment to study dark energy. Researchers can use sophisticated surveys and telescopes to map the positions and velocities of galaxies across the void, creating detailed three-dimensional models of its structure. This allows scientists to simulate the void's evolution over billions of years and compare observations with predictions from cosmological models. Studying the Boötes Void is not just about understanding the void itself. It also sheds light on the broader cosmic web. The universe is structured like a vast network, with dense filaments and clusters forming nodes in this web, and voids filling the spaces in between. The Boötes Void exemplifies the extreme end of this distribution, representing a nearly pure underdense region. By studying its boundaries, where filaments of galaxies begin to appear again, scientists can better understand how matter organizes itself on cosmic scales. The contrast between the emptiness of the void and the dense structures at its edges helps illustrate the dual role of gravity and dark energy in shaping the universe. The Boötes Void also has philosophical and scientific significance. From a human perspective, it is almost unimaginable to think about such an enormous region with so few galaxies. If a civilization existed within a galaxy at the center of the Boötes Void, its night sky would be dominated by darkness. The nearest visible galaxy outside its own would be millions or even hundreds of millions of light-years away. This extreme isolation underscores the long-term consequences of cosmic expansion driven by dark energy. Observing the Boötes Void gives us a glimpse into the distant future of the universe, where similar empty regions may become even more dominant as expansion continues to accelerate. Researchers also use the Boötes Void to test alternative theories about dark energy and cosmic structure formation. For instance, some models suggest that dark energy might not be uniform but could vary depending on location or time. The predictable environment of the Boötes Void makes it an ideal place to search for such variations. If the galaxies inside the void are moving apart faster or slower than predicted, it could indicate that dark energy behaves differently in low-density regions than in dense clusters. Additionally, the void can provide clues about the initial conditions of the universe. Its size and emptiness may reflect the density fluctuations present shortly after the Big Bang, offering insight into the earliest moments of cosmic evolution. Observationally, the Boötes Void is a challenge. Its vastness and sparsity mean that detecting galaxies within it requires sensitive instruments capable of capturing extremely faint light. Large telescopes equipped with advanced detectors are used to measure redshift and map the distribution of galaxies, revealing the internal structure of the void. These observations are combined with simulations that model the effects of dark energy, allowing astronomers to predict how the void will evolve over billions of years. Such studies are essential for testing the accuracy of cosmological models and refining our understanding of the universe's expansion. Furthermore, studying the Boötes Void can help improve our understanding of galaxy formation and evolution. Galaxies within voids often differ from those in denser regions. They may have lower star formation rates, fewer interactions or mergers, and unique structural properties due to their isolation. By comparing galaxies in the Boötes Void with those in clusters and filaments, astronomers can explore how environment influences the development of galaxies. The extreme isolation of void galaxies provides a natural experiment in cosmic evolution, showing how galaxies evolve when free from frequent interactions with neighbors. Boötes Void serves as a natural laboratory for exploring some of the most profound questions in modern cosmology. Its enormous size and extreme emptiness make it ideal for studying the effects of dark energy, understanding the growth of cosmic voids, and observing galaxy evolution in isolation. By tracking its expansion, mapping the distribution of galaxies, and comparing observations with theoretical models, scientists can test the uniformity and behavior of dark energy. The void also offers a window into the history of the universe, revealing how matter has organized itself over billions of years and providing a glimpse into the future of cosmic expansion. As one of the largest and emptiest regions known, the Boötes Void continues to captivate astronomers, providing a rare and valuable opportunity to study the universe in one of its purest, most isolated forms. The universe we inhabit is not static. It is an ever-changing, dynamic entity. From the earliest moments following the Big Bang to the present day, space has been expanding, carrying galaxies along as the cosmic fabric stretches. This expansion, once thought to be slowing due to gravity, has been revealed through modern observations to be accelerating, driven by the mysterious force known as dark energy. While we currently observe a universe filled with galaxies forming clusters, filaments, and voids, the far future promises a profoundly different cosmos, one dominated by isolation, emptiness, and the gradual disappearance of the familiar structures we see today. Understanding this future requires exploring the long-term consequences of continuous cosmic expansion and the impact it will have on galaxies, voids, and the very nature of the observable universe. If the expansion of the universe continues indefinitely, the first and most dramatic effect will be the increasing separation of galaxies. Currently, galaxies within gravitationally bound groups or clusters remain close to one another because gravity is strong enough to resist the pull of expansion. The Milky Way and the Andromeda Galaxy, for example, are expected to collide in about 4 billion years, merging into a single larger galaxy despite the overall expansion of space. However, galaxies that are not gravitationally bound, particularly those at large distances, will continue to drift apart. Over billions of years, these galaxies will move so far from each other that the light they emit will take exponentially longer to reach neighboring galaxies. Eventually, this light may become so redshifted that it stretches beyond the observable range of any conceivable detector. To civilizations or observers within a given galaxy, these once visible galaxies will effectively vanish from sight, leaving only the local cosmic neighborhood illuminated while the rest of the universe fades into darkness. This gradual disappearance of galaxies from view is not merely an aesthetic change, it fundamentally alters the structure of the observable universe. The observable universe is defined by the distance light has traveled since the Big Bang. As expansion accelerates, the distances between unbound galaxies increase so rapidly that many will cross what is known as the cosmic event horizon. Once a galaxy passes this horizon, its light can no longer reach us, no matter how advanced future technology might become. From the perspective of an observer, the observable universe will shrink in relative terms, even as space itself continues to grow. Over tens or hundreds of billions of years, entire regions of the universe currently teeming with galaxies will disappear beyond this horizon, leaving isolated islands of matter scattered across an ever-darkening cosmos. The cosmic web, the vast network of filaments and clusters that connects galaxies across the universe, will also undergo profound transformation. Presently, gravity pulls matter into dense filaments that intersect at galaxy clusters, leaving vast, empty voids in between. As expansion accelerates, these filaments will stretch, elongating the connections between clusters while thinning them out. Over immense timescales, the filaments may become so tenuous that the clusters appear as isolated nodes, with the once continuous cosmic web broken into disconnected islands. The contrast between dense clusters and empty voids will intensify, creating a universe dominated by sparsity and isolation. This thinning and fragmentation of the cosmic web will leave voids, already enormous and dark, growing even larger, swallowing more regions of space as the expansion accelerates. The Boötes Void, one of the largest known voids, provides a glimpse into this future, serving as a template for what many parts of the universe may look like billions of years from now. Galaxies within voids will experience the most extreme form of isolation. Currently, even within voids, a few scattered galaxies exist, forming tiny islands in the vast emptiness. As expansion continues, the few galaxies within these voids will drift farther apart from one another, increasing their isolation. Eventually, each galaxy may become the sole representative of matter in its surrounding region. Gravitational interactions with distant neighbors will become negligible, and intergalactic communication, even through light or other forms of radiation, will become impossible. These galaxies will become cosmic archipelagos, existing in profound solitude, cut off from the broader universe. For hypothetical observers in these galaxies, the night sky would be overwhelmingly dark, punctuated only by their own stars and any remnants of nearby galaxies before they cross the cosmic horizon. The universe would appear finite and isolated, giving rise to a perception of cosmic loneliness that surpasses anything imaginable today. The long-term consequences of continued expansion also extend to the fate of galaxy clusters and individual galaxies. Clusters that are gravitationally bound will resist being torn apart by expansion, but their isolation from other clusters will grow. These clusters will effectively become separate universes unto themselves, surrounded by the infinite dark void of expanding space. Within clusters, galaxies will continue to interact, merge, and evolve over billions of years, but beyond the cluster boundaries, the vast emptiness will dominate. Even the most energetic processes, such as supernova explosions or gamma-ray bursts, will be confined to these isolated clusters, their light unable to traverse the accelerating expansion to reach other parts of the universe. Expansion will also affect the large-scale distribution of matter in ways that have implications for cosmic evolution. Dense regions will remain gravitationally bound, forming small pockets of structure, while low-density regions, the voids, will grow disproportionately. This imbalance will accentuate the contrast between the few luminous areas and the overwhelmingly dark, empty spaces between them. The Boötes Void provides an early example of this dynamic, with its sparse galaxy population already highlighting the dominance of emptiness in underdense regions. As time progresses, voids across the universe will expand in size and influence, becoming dominant features of the cosmic landscape. The observable universe will increasingly consist of isolated, gravitationally bound islands surrounded by vast seas of nothingness. The effects of cosmic expansion on light also have profound implications for the information we can gather about the universe. As galaxies move away from us, the light they emit becomes redshifted, stretched to longer and longer wavelengths. In the far future, this redshift will push the light from distant galaxies beyond the visible spectrum and eventually beyond the detectability of any conceivable instruments. This means that future civilizations, even if technologically advanced, may be unable to observe evidence of other galaxies or infer the true size of the universe. The observable universe will appear smaller, not because space itself is contracting, but because the expanding voids prevent information from distant regions from reaching observers. In essence, the accelerating expansion erases the cosmic horizon, creating a future in which each galaxy or cluster exists as an isolated, self-contained universe. Another consequence of the accelerating expansion is the ultimate fate of the cosmic web itself. Filaments connecting clusters, already stretched thin, will continue to elongate and fragment. The connections between clusters may break entirely as intervening space grows faster than light can travel. Over tens of billions of years, the universe may transition from a connected network of galaxies into a set of independent nodes, each surrounded by a nearly infinite void. This process effectively transforms the universe from a rich, interconnected system into a sparse collection of isolated structures, dominated by the empty space between them. The far future of expansion also has profound implications for the study of dark energy. Observing the rate at which voids expand, filaments stretch, and clusters separate provides critical insights into the properties of dark energy. If dark energy remains constant over time, the acceleration of expansion will continue at a predictable rate. But if it changes or behaves differently in low-density regions versus dense clusters, these patterns of isolation and void growth will reveal those variations. By studying extreme examples like the Boötes Void and projecting their behavior into the future, cosmologists can refine their models of dark energy, improving our understanding of the universe's ultimate destiny. In this future, life and civilization, if they exist at all, will face unique challenges. The isolation of galaxies will make intergalactic communication or travel effectively impossible. The resources of an isolated galaxy or cluster will become finite and self-contained, requiring extreme efficiency and long-term planning. Observers in these galaxies may perceive the universe as fundamentally empty, altering philosophical, cultural, and scientific perspectives. The accelerating expansion forces a shift from thinking about a connected cosmos to understanding a universe where isolation is the norm. The far future of cosmic expansion is a story of isolation, emptiness, and profound transformation. Galaxies will drift apart until their light can no longer be observed, shrinking the observable universe and creating the perception of an increasingly lonely cosmos. Filaments of the cosmic web will stretch and eventually break, voids will grow larger, and galaxies within these voids will become eternally isolated. Gravitationally bound clusters will remain islands in an expanding sea, while the vast majority of space will be dominated by accelerating emptiness. This vision of the future, informed by the current understanding of cosmic expansion and dark energy, highlights the transient nature of structure in the universe and underscores the extraordinary scale and power of the processes shaping the cosmos. The far future of cosmic expansion presents a vision of the universe that is both awe-inspiring and profoundly isolating. Unlike the familiar night sky we see from Earth, filled with countless stars and galaxies, the universe billions or trillions of years from now will look drastically different. This transformation is driven by the continuous and accelerating expansion of space, a process propelled by the mysterious force called dark energy. Today, galaxies appear connected through the cosmic web, a vast network of filaments linking clusters and superclusters. But in the far future, these connections will stretch, thin, and eventually vanish as galaxies drift further apart. Currently, gravity binds galaxies into clusters, ensuring that they remain relatively close despite the expansion of space. The Milky Way and the Andromeda Galaxy, for instance, are expected to merge in several billion years, forming a larger galactic system. However, galaxies outside such gravitationally bound groups will continue to recede from one another at ever-increasing speeds. Over immense timescales, light from these galaxies will become so redshifted that it effectively disappears, slipping beyond the cosmic event horizon. From the perspective of an observer within a galaxy, these distant galaxies will vanish from sight, leaving only the local neighborhood illuminated. This shrinking observable universe emphasizes the isolation and solitude that will define the cosmic landscape in the far future. As expansion progresses, the cosmic web will undergo dramatic transformation. Filaments connecting clusters will stretch like elastic threads, thinning as space itself grows. Eventually, these structures may fragment, leaving isolated clusters and individual galaxies suspended in an increasingly empty void. The Boötes Void, one of the largest and most underpopulated regions in the present universe, provides a preview of this lonely future. The emptiness within these voids will continue to grow, with galaxies inside them becoming isolated archipelagos in a vast, dark, cosmic ocean. This intensification of isolation is a natural consequence of the accelerating expansion and the weakening influence of gravity over large distances. The implications of this future extend beyond mere visual transformation. The disappearance of distant galaxies will restrict the information available to observers, effectively erasing large portions of the universe from measurable reality. Even highly advanced civilizations, if they exist, will be confined to the resources and matter within their isolated galaxy or cluster. Philosophically, this extreme solitude may alter perceptions of existence, fostering a sense of cosmic loneliness and influencing cultural, scientific, and societal development. The universe is not static, it is dynamic and ever-changing. The accelerating expansion driven by dark energy will ultimately transform the cosmos into a collection of isolated islands amid an ever-growing emptiness. Observing this process today allows scientists to predict the future evolution of galaxies, voids, and cosmic structures. Billions or trillions of years from now, the universe will be vast, hauntingly silent, and profoundly lonely, a testament to the immense and ongoing forces shaping all of existence. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.